Morning. Welcome to, is anybody in here who's not here for 385 Advanced Digital Systems? All right, let's get started. I'm Dr. Morrison. I'm your professor this semester. Has anybody not turned in the extra credit assignment? Please turn it in right now. Anybody who's not, because we are locking in, if you have the extra credit assignment, please start. Basically, the way it works is I'm going to have daily homework assignments. Those of you who did this already know. I did say on chair because usually I have to pull up a chair, but then we have a nice handy desk this year, so I'm happy. Basically, come up here, just put it in front. If once I start lecture, if you come in late, just hold on to your assignment and wait until the end, and we'll talk about. Just come up to me afterwards, and we'll have a discussion about what happened. If you're running late to lecture for any reason, does anybody not have one of the smartphones now or any other way to quickly contact me if for some reason you're on the bus and it breaks down or something like that? No? All right, cool deal. So just shoot me a message. If you send me a message before lecture, we won't have any problems. It's if you where it become an issue is if you become a habitual line stepper and you consistently come to class late, consistently don't turn in your assignments, and then we have problems, okay? So that's where I'm going to start kind of putting my foot down. So I'm consistent but fair and understanding about the policy. Anybody else? Going once? Going twice? Sold to the man in the electrical shirt. So, all right. So I'll quickly go over the syllabus, and then we'll talk about the new University of Mississippi attendance policies. Particularly regarding coming to class and taking the plagiarism quizzes. And we'll go into the fundamentals of the stuff that we're going to be covering in this material. What is a digital system? I mean, you guys have taken digital systems. We're going to do some review, talk about how that applies to computer architecture and computer organization. And we're going to talk about this concept of small-scale integration to very large-scale integration at the transistor level and how that applies to what we're doing. And then we're going to go into combinational and sequential logic. Okay, so I started out the video with the same cartoon. If you want to get inside the head of all of your TAs or professors, there's this great website called PhD Comics, and they think it's funny. You might not, but it's a good insight. And so every professor, TA, has had to deal with this thing where they're busy and they're starting to get harassed by students. Like, well, what does the homework do? What's the test? And it's all in the syllabus, right? You see her, she's about to go crazy. So. Like I said, professors find it a lot more funny than students do. But anyway, my office is 310 upstairs. Monday, Wednesday, and Friday, 1 to 3, or by appointment. George Humphrey, he is my teaching assistant for this semester. Here's his contact information. The required textbook is Patterson Hennessy, and the recommended text is Koenig and Ritchie. These are two of the foremost textbooks in computer science and computer engineering. So it's very good. Oftentimes when you'll interview for jobs, companies will actually ask you to obtain a copy of Patterson Hennessy and read up on it, and they'll ask you questions from that. So one of the goals for having these topical guide objectives is for you to quickly and rapidly get that information instead of having to repurchase the textbook. And Koenig and Ritchie are the two people who invented the C programming language. So who better to teach it, right? Last year I taught the course in VHDL based on student feedback on the curriculum, and I switched it to C. So hopefully there'll be a lot of focus on programming concepts, programming fundamentals, how to do a procedural language, and how that will eventually help you improve your object-oriented programming. Generic grade scale. Quizzes, homework assignments, C projects. I've included this upon completion of a course you may credibly claim on a resume. I have a folder on Blackboard that's titled Professional Development. I don't want you to come in here and just try to get a grade. I want you to start building towards the process of getting a job, because that's why you're here, right? You're not here to listen to me at 9:30 on Tuesday and Thursday, right? You're here because you eventually want to get a job that pays well and you can buy food and be happy, or at least get closer to it, right? You're not here because you like me so much. So this is we're going to talk about how do you look at a job description, how do you actually tie this to a resume and make your resume look professional quality. So this is these are the technical tools and skills you will learn in this course. You will gain extensive knowledge and principles of these digital systems techniques. Skill in communicating, writing technical information. When you apply for jobs, a lot of times they will give you the ability to upload sample code and sample projects. You put everything in your folder, you have your project descriptions, you have your project code. It's going to be well commented because we're going to go a lot into commenting code principles. And put that up there. Not only can you just say that on a resume, you can actually prove it with your schoolwork. And then your projects, you'll be in groups of 3, and you'll be designing, simulating, and synthesizing a register transfer level of a MIPS 32-bit data path. That will all make much more sense in C. And then a lot of this, as you can see, this is the Accreditation Board of Engineering and Technology. This proves that we have done this course to make sure that your degree is still valuable once you leave. MSI is medium-scale circuits into larger and more complex circuits. Being able to design projects in C, write a C description of combinational and sequential logic. Using engineering software to compile and simulate circuits, and so forth. Understanding the relationship between hardware architecture and a computer's assembly language instruction set. All these are very important in being able to take the code that you're writing and implement it on an advanced digital system. Okay, so kind of briefly gone over my attendance policy. Be on time, submit your assignments on time. If you're running late, send me an email. Don't be a habitual line stepper, come to class. I as you saw, I do the recording. I post all the recordings of lectures on YouTube. So for some reason, I did get an email from a student who has to miss next lecture because of a job requirement. So they emailed me, that's fine. Go to the YouTube, submit both the homeworks that you missed for that day. And that's square away, right? Very simple. But I still want you to come to class. You get that first time where I lecture, you work on the topical guide objectives, you look on the video. Now you've had 3 opportunities to practice, right? So now automatically, the reason I do it this way, I was in the Navy. I was in the nuclear Navy, the nuclear power program, and topical guide objectives were how they managed to cram 4 years of material into 6 months. I went to the University of South Florida, and our Dean of Engineering, he was giving this talk to the TAs. He's like, you have this many students, but only this many quality. You have to learn how to lower your standards when grading. And I was like, no, I'm going to teach more students how to be successful. My goal is that I want you to be outstanding students and take those principles of study and how do you turn those into being successful engineers. And I can tell you right now, the course that we cover, when you compare the similar courses at MIT, Stanford, you will cover more and you'll go in more detail and you'll get better grades because we've done the comparisons in the past. So by the end of the semester, my vision is that you will be the best advanced digital systems course in the world. This group right here, you'll do it. And I said last semester, everyone got intimidated, and then we did the comparisons, and they won. So you'll do it. So that's why I asked for the hard work, but you'll be rewarded. Topical guide objectives, we've gone over that. My course policy, this is important. I want to reward hard work. Failure to earn a 70% on TGOs will earn an automatic D or worse in the course, but you'll see that I've never had anybody who consistently submitted who got below an 85%. So as long as you consistently submit, consistently do your work, it's not going to be an issue. I went over on the video why I insist they're handwritten. Quizzes, I will have 4 pop quizzes. Here's the policy on pop quizzes. 50% of the pop quiz for the points is you are here in the room and you showed up, right? So by putting your name on it, you automatically get 50 out of 100. So that takes a little bit of the burden of, I fell behind a little bit in studying, and you showed up and you make a solid attempt on the exam. On the quiz. It gives you an opportunity to be honest with yourself about where you're at. And also, sometimes it's, from a professor's side, it kind of separates my A pluses from my A's, so to speak, But more importantly, you go and like, I thought I really knew this, and it turns out I don't, right? So then you go back to studying, and that's why come exam time, the typical median score will be somewhere between 88 and 91%, because you'll be very well prepared for the exam. Classes began yesterday. Your last day to withdraw is the 7th. Last day to withdraw and be able to get a refund. Last day to withdraw at all is October 5th. You'll have on October 4th, I send emails to every student telling you where you're at, so you can make an intelligent decision about whether or not you want to continue to tolerate me. Thanksgiving break. Final exam will be on the last Tuesday of that week. And on Thursday of that week, I will have your grades up to that point. You will still have your final project due that Saturday. I chose that due date specifically so you can get it done, be done with the class, and focus on the rest of your finals. I have a pizza party at the end of the semester. Everybody comes in, get a couple pieces of pizza, and then what I do is I'll have your grades printed out, and I'll call you up one by one. I'll look you square in the eye. This is an integrity part from as a professor. I'm going to be making some sort of determination on your future, right? So it's important that I should be able to look you square in the eye and say, this is the decision I've made on your grade, so that way you can carry forward. And then you also get pizza and you get to relax and not have to worry about all the other finals. So let's see. So this is just the general course outline. See projects. Last year, how many of you are planning to or are rushing a fraternity or sorority this semester? Okay, one. All right, so that was that was a lot different than last year. Last year I had about 7 or 8 who were rushing, and I chose due dates that apparently were the worst. If I had gone through their schedule to be devious, I picked the wrong one somehow. So I have picked these due dates to kind of avoid specific dates on the rush calendar, so that way you can meet those rush obligations and continue to excel in class. The final project, part 1, is I have different parts of here's how you're actually going to lay out your design. You'll have actually made all the other parts that you will need to build the full data path. Part 1, you'll actually draw everything out. Part 2, you'll describe how you're going to do it in C code. And then on that last Saturday or Friday, you'll actually have submitted your actual code and your project description. So you'll actually have completed an entire project design process. Incomplete, I'll give an eye in case of personal or family emergency. For religious observations, if for some reason you need to miss class due to religious observation, you need to let me know by the second week of class. Academic integrity, here's my course policy. And I have a whole list of things that are don't cheat, don't use common sense. First incident, I'll require you to write a 1-page report on an incident in something in engineering history where people's lack of commitment to integrity resulted in some sort of catastrophe. Kansas City Marriott walkway collapse, the Challenger explosion, Ford Firestone. Unfortunately, there's a lot of incidents, and since we're on the second floor and there's 4 floors in this building, we're dependent on the fact that the engineers told the truth that they actually properly built the other 2 floors of the building, right? So in computer engineering and electrical engineering, cars have a lot of sensors. They have all the different communications that go and be able to properly monitor the vehicle, right? You don't want to suddenly go off and the brake doesn't work and suddenly you smash it or drive off a bridge. Right? So second incident, you'll just receive an automatic F in the course. So the rest of this, I took a lot of that stuff from the M book. You can feel free to look over that for any kind of details. Now, does anybody have any questions about? There are 7 students who have yet to either take the plagiarism quiz or get a grade of at least 7 of 8, which I believe is an 88%. I'll send out emails to everybody who has yet to do that. The new University of Mississippi attendance policies, I'm sure you saw the goofy videos they're posting everywhere. Basically, I take attendance. If you're not coming to class, I can unenroll you. Other things, if you haven't taken a plagiarism quiz, I can unenroll you for that too. So just get it done. It takes 15 minutes. And does anybody have any other questions about any course policy that I have before we go forward? All right. So, what is a computer? Is there electrical engineers who want to study advanced digital systems? Eventually you need to know what a computer is, right? So you're going to have your underlying hardware. So we're going to be talking a lot about how do you actually design flip-flops and turn those into memory elements, and then turn those memory elements to memory arrays, and then turn those memory arrays into data memory and instruction memory. You can use that to build cache memory, right? So you have a lot of hardware, your arithmetic logic units, and then from there you have system software where you have your operating system, your Windows 10 or your Linux system, compiler and assembler. So you're taking code and you're compiling it down to this what's known as assembly language, which we'll go into a lot in this course. And in assembly language converts it to machine code. So machine code is actually where you have your zeros and ones. So in the MIPS data path, which is a 32-bit data path, every instruction is going to have 32 zeros or ones, and those are all going to mean something to the machine. And then we're going to learn how the machine processes that. And the reason why C is a good programming language is that it was specifically designed to be taken from the compiler down to the machine code and done fast. The understanding advances of systems, specifically as electrical engineers, being able to have high performance is an important aspect of computing. And then from there, programs users, so you basically have Office like or Adobe PDF like we're running, or any other program that you happen to be running on your computer. So since the 1970s, when Intel released their 4004 processor, the chip density has been steadily increasing. And it has continued along this path all the way up through 2015. Does anybody, what is the name of this phenomenon that I'm describing here? Moore's Law, right? And so is that actual physical law of science? No. Who is Moore?
Is it Intel engineering accountant?
Yeah, because Gordon Moore, he was one of the two founders of Intel, right? And so he noticed that the employees, when they were designing their chips, they were following along every 18 months, they were essentially doubling the chip density. Okay? So he said, this is our standard we've now set, we need to keep that. So Moore's Law is actually just a challenge to his employees. And by doing that, you have to worry about this thing called feature size. So feature size is the actual size of the transistor. So basically, there is, I don't know how many of you have studied anything about transistors? Just a little bit. Okay, so a CMOS transistor, you have a gate and source and a drain, and there's a different space between the gate and the drain. And that's what's known as the poly length. And that poly length is also is half of the feature size. So basically, the feature size describes how small the transistors can be. So as the chip density is increasing, we're also simultaneously getting this steady decrease in feature size. So you go from 0.23 micrometers down to 0.18 micrometers down to 90 nanometers down to 45 nanometers, 22 nanometers, and so you're seeing different technologies where they're hitting at like 12 nanometers or 7 nanometers. Intel's Ivy Bridge, the new computers they're rolling out, are currently at 22 nanometer. And so here's the problem. When you start putting a bunch of chip transistors together really, really tightly, and they're consuming energy, and they have electron flows from the gate to the drain, you start consuming a lot of energy. If you ever go to Intel presentation or take any other class where they're using Intel material, you'll see some variant of this particular slide where you have 4404 and it's watts per centimeter cubed, and it's not that hot, and suddenly you're dealing with Intel Pentium Pros, and now you have to really worry about cooling. And once you start worrying about cooling, then you get to the point where the Pentium 4 without cooling would get as hot as a nuclear reactor, and eventually you start getting up to the sun's temperature, right? So that's not going to be very good if you have your laptop, you put it on your lap, and suddenly it's as hot as the sun. You're a goner, right? So these are kind of things that you have to worry about. You don't want it running fast. If you're running fast, you're having a lot of switching at the transistor level. If you have a lot of switching at the transistor level, that causes more power consumption, heat, and therefore you have this issue. So we're going to be learning a lot about the trade-offs in performance and reliability of a system. And so we used to start with these carbon nanotubes and getting down to what is known as system on chips, SoCs. And so as technology gets smaller and smaller, it used to be, and we're going to talk about we're going to talk a little later today about something called the tyranny of numbers. Are you guys familiar? You're familiar with JK flip-flops? We're going to review those in class. Does anybody know what JK stands for? JK stands for Jack Kilby. He's an engineer at Texas Instruments who invented the JK flip-flop. He also came up with the solution to this problem called the tyranny of numbers. People used to think, you remember those days to computers the size of a room? The reason why is because everybody thought that every part of the computer had to be connected to every other part of the computer. So Jack Kilby, he realized that if we just have a program flow, a data path, we can significantly reduce the size of the computer. And he's also the inventor of the silicon chip. So he is the only electrical engineer to win 2 Nobel Prizes in physics. So knowing who JK is very important. We're going to discuss that a little later today. So we came from these carbon tubes down to system on chips. And so this is actually one of the very first transistors right here too. And so we're going to be dealing a lot with silicon, but you kind of have a lot of future technologies that people are trying to make dominate past silicon. I'm actually doing some research with one of my research assistants on quantum computing, specifically this concept of magnetic QCA. It's pretty interesting stuff. But here, some one of my expert comments here. The irony of Moore's law is that designers assumed a constant improvement in technology size and thus have not properly accounted for their implementation technology in their digital design, hurting architecture improvement. This is Phil Elmo, chief scientist at IBM Research. So, why are you taking an advanced digital system? So you can properly account for implementation of technology at the advanced digital system level. So you can't just assume, as competent electrical engineers and very good electrical engineers will understand this concept, and you'll understand this at the end of this course. All right. So here's Jack Kilby. I was just telling you about him. They were unable to increase computing performance due to the huge number of components. And they thought that every other component needed to be connected to every other component. And here he will take this huge computer and quickly get it down to this computer chip that he's holding in his hand. Right? So he won the Nobel Prize in Physics for the silicon IC invention. Right? And so now we're going to start talking about what's actually going on here. So topical guide objective 1.1. So one is section 1.1, meaning that's the first advanced digital systems. Advanced digital systems. Right? Please come in. I won't bite. I can't speak for all of them yet. I just met them. So small scale integration. Logic circuits that use less than or equal to 10 transistors. Medium scale goes up from 10 to 100. Large scale integration goes from 100 to 1,000. And very large scale is anything larger than 1,000 transistors. And the reason why this is important, other than just knowing, how to multiply by 10 to different levels, is that when you're designing at the SSI level or the MSI level or the LSI level or the VLSI level, that requires very different designing techniques. So if you're designing, this example I have, I'm going to scroll up just a little bit so those in the back can start seeing the TGO. At the bottom here, it's an example of SSI is a 2-transistor inverter in CMOS. So the idea is that you have a PMOS transistor. So those of you who can't see it, I'll draw up here. So you have what's known as VDD, so that's the supply voltage, and that's equivalent to a logic 1. And you have a PMOS transistor, positive metal oxide semiconductor. Negative metal oxide semiconductor is an NMOS, and you have an input. So you're converting an inverter, right? So you have logic A, that we're going to call O for logic out. So if logic A is 0, here's what's happening. We want the 1 on the output, right? So what's going on here is you put 0 on the input. It's going to be put on both the NMOS and the PMOS transistor. Without getting too much into the physics, for those of you who want to take 482 next semester with me, we'll go into much more detail about how this is done. But for right now, just press the big old I believe button. When you put a 0 on the NMOS transistor, it shuts off, meaning the flow cannot go through. When you put a 0 on the PMOS transistor, the flow will go through, and it will go from your supply voltage, which is a logic 1, to the output, which is how you get a 1 on the output. Likewise, when you put a 1 on the input for a PMOS, it shuts off. We put a 1 on the gate for an NMOS, it turns on. Therefore, your ground voltage goes to the output. So that's how you're able to invert a signal. So coding at this level requires a lot of understanding of the physical implementation. And being able to actually properly design transistor layouts. How do you deal with certain race conditions? How do you deal with certain parasitic capacitances, things at that level? When you start getting to MSI, and does everybody have 1.1? Give you a split second. When you get to MSI, that's where you start taking transistors and you build gates, you build AND gates, you build OR gates, and you start trying to combine them into like full adders at that level. So you got 10 to 100. Okay? So I'm going to start scrolling down here a little bit. So here you have AND gates, exclusive OR gates, inverters, and you start converting to an arithmetic logic unit. So for large-scale integration, you're taking those MSI devices that have been properly designed. You have an arithmetic logic unit, you have an adder. This is what's known as the MIPS 32-bit data path. So basically, instruction memory, you have a lot of SRAM and DRAM. Once you have SRAM and instruction memory, SRAM registers, and you're going to have cache memory for your access with DRAM. The whole idea is that you generate a 32-bit instruction. You make a number of decisions. I actually don't like this diagram because it's not an adequate description of the data path. We will go into much better descriptions later in the course. You access some registers, perform some operation on them, and then you store it. That's a very simple description here. But now you're taking all these MSI elements and building it into an LSI element. So this is a LSI implementation here. And then a very large scale integration is where you start getting into your Intel processors. How do you take this and interact with cache hierarchy? How do you take this and interact with I/O? How do you take this and interact with all of your other elements of your devices? This is where you get to very large scale integration. So designing at all of these different levels requires different coding techniques and different ways of thinking, which is kind of what Phil Emma was talking about. A lot of people who are coding at the VLSI level and MSI level, the LSI level, don't really think about the transistor very much. And as a result, they kind of just assume that the Moore's law will be satisfied at the transistor level. We're going to be learning a lot about Amdahl's law, performance improvement, and you can have different ways to actually improve this without having to worry about the underlying technology. And so, kind of going into a little bit about, remember, combining MSI circuits to VLSI circuits. So that's how we're going to meet objective 1 of the course. Additionally, kind of a brief overview of CMOS. The important thing to remember is that CMOS has significantly smaller and fewer components. You're able to have this project flow, kind of like Jack Kilby came up with. And when you start, most of the cost on synthesizing chips comes with the first 10,000. Once you're able to roll them out, the cost is effectively the same at 10,000 versus 10 million. So a lot of the cost is in design and implementation. So if you want to be an advanced digital system designer and you want to save your company a lot of money, you can be really good at it and help out quite a bit. So effective advanced digital design saves cost long term. All right, so you scroll down here. If you are taking an advanced digital systems course, I believe that you should be able to adequately define what is a digital system. So you should definitely know this. Everybody catch that? Wink. Hey, if I'm drawing stars and I'm saying you should definitely know this, what do you think that means? Yes, and when specifically should you know it? So like quizzes, tests, right? You'd be surprised how many, I asked the whole room, what's JK stand for, and not one of you knew the answer. You've been through a digital systems course, right? The number of times people are like, I can't believe how many people don't know who Jack Kilby is, and learn these things and remember them so that way you get in, people start asking you questions when you get to a job and you don't have this blank look on your face, what's going on? So we define a digital system here as any circuit that takes in a set of discrete information inputs and discrete internal information system state, and either generates a set of discrete information outputs or stores them as information. I'll read that one more. Okay. So here's what that means. You have some sort of stored memory elements, right? That's your system state. That's your current system state. And you have some sort of inputs. Those inputs can be control signals. They can be data values. And based on that, you can have some sort of Mealy and Moore machine. And then you produce a discrete set of outputs, and you update the memory. So that's where, so the discrete inputs and discrete digital, right? And discrete internal information, system state, either generates a set of discrete outputs or updates the memory. So we're going to talk about a lot about the difference between R-type instructions and load word and store word instructions. What that generally means is R-type is anything where you take two inputs to arithmetic logic unit, perform an operation, and then store it in the local registers. Whereas load word and store word is you're taking elements from the cache data memory and storing in the local copy, and store word is taking your updated local copy and storing it in the cache. So being able to understand the system state and how this all works at the MSI level also applies to the LSI level and VLSI level. All right. So once you know the difference between combinational and sequential logic, TGO 1.3, combinational logic system has no state present, has no memory elements, right? Has no state present, therefore the output is a direct result of the digital system's function. Inputs, function, outputs, like algebra 1, right? So, and here's kind of this definition, function output equals a function of input. So I've included a couple of examples. Is multiplexers. That's a 2 input, 1 output structure, right? Where you have 2 inputs and the multiplexer selects which one. Encoders and decoders, you can actually have 4 inputs and 2 outputs. You can have zeros. One of the 4 outputs, if you have one of the 4 inputs, if you have 2 outputs, you can either have 0, 0, 0, 1, 1, 0, and 1, 1 correlate to which particular input you want. So you can use that to encode. And if you have like 1, 1 on a decoder, you can actually just have a 1 go out on the output of the 4 output signals of the decoder. So you can actually use this combinational logic to simplify information when you don't need to save it. And then I'll scroll up, but for those of you, so drawing a sequential element, a sequential logic system, TGO 1.4, has present state. The output is either a function of the present state or the present state and the input. And we'll go into why that's important to be able to differentiate between those. So let me scroll up here. Again, a sequential logic system, this is the description, has a present state, so it's memory element, has some sort of initial present state. The output is either a function of the present state, meaning that every time there's a clock pulse or every time it changes, it produces a new output based on the present state, and then it's updated, or the present state and the input, meaning it receives some sort of input, meaning if it's a 0, stay the same, if it's 1, do something different. Anybody think of an example of a present state and the input of a memory element or that you've studied in digital systems? Yep, flip-flops. So, of course, I have the answer right here, so we can just read three lines down. So we'll talk about master-slave flip-flops, D flip-flops, edge trigger, D flip-flops, T flip-flops, and JK flip-flops. And registers, there's a set of N flip-flops or SRAM devices that are used to store elements in a 32-bit data path. Each register contains 32 dual-read, single-write SRAM. And we'll talk a lot about what that means and why it's important it has dual-read but only single-write. And all that dual-read, single-write has control signals, which involves the function of the present state and inputs. Does anybody have any questions about the definition of sequential element? Okay, up. So 1.5, if the state of the sequential logic system is updated at discrete times, then it is synchronous, meaning that it cannot be changed until it receives some sort of clock pulse. These are known typically the edge-triggered flip-flops, right? You know, a lot of those times you have to wait until a specific clock pulse happens, and it will take the specific moment that the edge occurs, and that's how it will update the flip-flop. Otherwise, it just won't do anything. If the state may be updated any time, then it is asynchronous. So, what do you think some of the pros and cons of synchronous and asynchronous devices are? Nobody? They're all the same. All right, general view. Asynchronous devices typically require less area and consume less power because you don't have to worry about controlling it for the clock signal, right? That requires more area, consumes more power. However, you have to worry a lot about things called race conditions, which we'll study about a little later. Which basically you don't want the value of a specific output reaching before the value of another output. So let's say I'm adding two numbers, and I have just some sort of 4-bit adder, right? And my A input, they're supposed to arrive at the same time and perform some sort of addition, right? Let's say I have a race condition, and as a result of the race condition, this value here is briefly 1 instead of 0. That's going to give me a wrong output. So you can use synchronous elements, and we'll discuss this later, when it's appropriate to use which one. But basically, you want to, any situation where situation like this may occur, you don't want to use asynchronous circuits. And it would flip back, but then you get weird values, and especially if you're doing something like cybersecurity or banking, where you're expecting a number to be a 1 instead of a 0, suddenly you have a lot less money. That's not good, right? So to design synchronous sequential elements, we have to worry about these things called finite state machines. So we define an FSM as a mathematical model of computation used to design both computer programs and sequential logic circuits. So basically what this is the mathematical model for how sequential elements work. And so you can actually use FSMs to design computer programs because, for example, FSMs are used to run your Coke machines or your vending machines that you'll see in the union, right? So basically, you have a finite state where you start, and you have to meet a certain number of requirements, put in a certain amount of coins or swipe a card before you can actually vend, right? So if you put in 5 cents, if you try to vend, it'll say it's not ready. So then you have to worry about, you can also put in 10 cents initially, you could also put in 25 cents initially, or you can put in $1 initially, right? So from there, you have to worry about all the different possible combinations. The most efficient way to do that is to use a finite state machine. Similarly, you want to be able to have logic values, and we're going to cover Mealy and more machines, that dictate how the sequential element works. And by reducing the finite state machine, you can actually reduce the overall area of the element, and allows you to consume less power and be more efficient and do the exact same logical calculation. And so, as I've kind of gone over before, we formally define a state here as 7 is a state is all the stored information at the given instant of time to which the circuit or program has access. you have your normal combinational logic, you have your state, which is stored in your registers. And so that the reason why this definition is important is because it allows you to differentiate between present state and next state. Present state is the state you're currently in. The next state is what's going to result as when you perform your operation. So you get you have your clock signal. So this is a sequential logic structure that is synchronous. So it gets your clock signal, it sends its n inputs, and it has some sort of input value. Here's a really good example. You can use this to do multiplication. We're going to be learning about restoring and non-restoring division. We're going to learn about sign multiplication in this class. So you're going to have some sort of current value, and it's going to go in based on the, and you're going to, if you're doing 32 bits, you're going to do 32 times. If you think about typical multiplication, so if we're doing 18 times 21, right? You're going to have 21. First, you're going to be multiplying 1 times 8 and then 1 times 1, right? And you're going to perform a shift. So we're going to be learning about shifting, shift left logical, right? So now you do 8 times 1 is 8. You store that, shift, and then that shift is going to come out of your state register, and then you're going to have another set of inputs. The other set of inputs is 1. So then 1 times 1 is 1. And then you're going to shift again. That's where your 0 comes in. So 2 times 8 is 6. Store that, register, shift again. 2 times 1 is 1. But you also have a carry. So that's 16. 2, 3. Right? And then the whole time you're adding, how you do that? You're adding by having your present state. So you're constantly updating that information. So that's how you're using sequential logic to be able to perform arithmetic. So then it's 370. So what I have found in the past when talking to students about states is when you see textbooks, they all describe all the alphabet and all the symbols, and students typically have a hard time understanding that. Or not a hard time understanding it, but they weren't properly conveyed to them in the past. So Topical Guide Objective 1.8 is a description of what an alphabet is, as well as the input and output alphabets and the required symbols. So the alphabet is a non-empty set where its intended use in string operations shall be indicated. Now, how do we indicate that? With the input alphabet and the output alphabet. The input alphabet is a finite set whose formal notation is sigma. And then you have the same thing for the output alphabet. So your input alphabet in a digital system, what do you think that your input alphabet is going to be? What's that? Well, no. First of all, that's sigma. No, but basically what this means is it's all the possible inputs and all the possible outputs you can have. So in a digital system, what are your possible inputs? 0 and 1. And what's your output after that? 0. There you go. All right, you guys are paying attention. Good. So sigma is going to equal 0 and 1. Again, a couple of you can look 2 lines down. But here you can have sigma is going to equal 0 and 1. And then you have that equals 0 and 1 as well, right? Gamma is equal to 0 and 1. So that's what that sig notation means, is all the possible inputs are 0s and 1s, and all the possible outputs are 0s and 1s. Now, the next thing you're going to have is you're going to have TGO 1.9 here, a transition function. So when you think about it, we have some sort of combinational operation. You're going to have some sort of transition. You don't want the computer constantly do the same thing. The answer is always 42, right? You have to have some sort of transition function. So here, the transition function maps a state and the input alphabet to the next state. The transition function in finite state machines has a formal notation of t. And then the output function maps each state to the output alphabet. The output function in a finite state machine has a formal notation of g. Okay, let me scroll up just a little bit so that those of you in the back can see 1.9 and 1.10. So now we have some sort of input alphabet, 0s and 1s. We have eliminated that because we have a digital system. Now we have a transition function. We take in our input alphabet, and perform some sort of operation, and then we need to have a relationship between the output function and the output alphabet. Now, in situations where when you're doing coding where it's not going to be discrete, that becomes much more complicated and necessary. But what you need to remember is everything needs to be zeros and ones, and when you don't have zeros and ones in digital systems, you're getting So, does anybody have any questions about this? I think a lot of the understanding will come into play when I start describing how Moore machines and Mealy machines work. All right. So, your Moore machine is your FSM where it's solely determined by the current state. I'm going to define Moore machine and Mealy machine, then we're going to go into examples of what those are. So you have your FSM whose outputs are currently determined by its current state. It's a 6-tuple. That means you have your state, your initial state, your input alphabet, your output alphabet, your transition function, and your output function, right? So you have a finite set of states, like we were just talking about here. If you have a JK flip-flop, there's only 4 possible switches, right? 4 possible changes. So you're going to have a limited number of states. The fewer number of states you have, the smaller your implementation area. Smaller number of transistors, smaller number of power consumption. A start state, you always have to have somewhere you got to start, right? So the moment it starts, like for example, the moment you turn on the computer, this is a common mistake engineers make, or electrical engineers make, especially at the collegiate level. They forget to account for the fact that you have to turn the computer on at some point. And there's nothing to do. You have to have it turns on, it starts something, it has to have an initial state. That state is initialized by SO. And then you have your input alphabet and your output alphabet. Your transition function takes your states plus your input alphabet and comes up with the next state, right? And the result output function basically maps your states to the output alphabet. So basically what you have is you have a number of state transitions, and you have to relate them to the fact that it's a digital system. So for example, I'll draw up a very simple Moore machine. You have your input state. We'll call this state 0. And then we'll call this state 1. If it's 0, if the output, your state is 1, just stays in the same state. If it goes to 1 here, we'll call this 0. Call this 1. So this is your basic Mealy machine. Moore machine. So you have defined the reason why mapping the input alphabet to the function is important is because in order to transition, you have to stay, you can only have transitions in your alphabet. If we had like C here, some sort of variable C, it would be an invalid finite state machine because that's not in our input alphabet, correct? So anytime you get something that's outside the alphabet, you automatically have an error. And then likewise, when you have your outputs, they have to map to the output alphabet, which in our case is also zeros and ones. So if a Moore machine just requires its current state, then it follows that the Mealy machine is going to require the current state and the current inputs. So 1.12, so does everybody have 1.11? Or that was for? All right, so I'm going to scroll up to about here. And I'll just keep scrolling. So a Mealy machine, so this is 1.12 here, is a finite state machine whose output values are determined by both its current state and the current input. So you have your set of states. It's a 6-tuple again, so you have your set of states, you have your initial state, your input alphabet, your output alphabet, your transition function, and your output function, right? So your start state is an element of S, the set S. You have your input alphabet and your output alphabet. Now your transition functions are different, right? So here in the previously, you map the transition function. You have your state and your input alphabet, mapping a state and an input symbol to the corresponding next state, and an output symbol. Let me clear that up. Likewise, your output function is going to be mapping to your output alphabet by using that state and the inputs. So I'm going to have a little diagram here that's right below where you all can see where I'm going to illustrate the difference between these two. Does anybody have any questions on this so far?
I guess what the output state be equal to the transition state for the Mealy machine?
All right, so yeah, I'll answer that question in more detail in a second here. But you're going to have an output state where you're going to be outputting some sort of value and updating the memory. So, give me 2 seconds. I have a drawing that describes it in more detail. So. Okay, so I'm going to scope about halfway through the Mealy machine TGO here to the transition function. So the first one we have here is our more machine. So we have our set of inputs, right? And then we have combinational logic. So we take our inputs here into the more FSM. So it's where we start our initial states, right? The output is going to indicate the next state. So we make some sort of decision, and based on that, we're going to update registers. So it stores the state information, and then it's going to start again, right? So the Mealy machine is going to be different. We're going to actually see a difference in how this combinational logic on your output is determined, right? So basically, if every state I say print some value, right? So that finite state, here I'll draw one up for you, see if I can. So again, I draw the finite state machine, 0 and 1. Okay, so basically what this one does, and here's our start state. So basically what's going to happen here is you start, you get to this state, and then you're going to make a transition to the next state, right? So your transition is here. Right? So this transition is the same as this portion of the diagram. And then you're going to store your state information. So now I'm in 1, right? And based on that, that's where you're going to perform some sort of operation. So when you're in this state, you're basically saying, I want to do X. So coming back to our original one, if I go to state 25 cents, I'm not going to go to state vend. I'm going to wait until they put in, I'm going to hold and wait until somebody puts in the next coin, right? So that's how that works. So then what's going to happen is you're still here. And let me go. So when you make this transition, what this means is now you're updated the next state information to the current state information. And then what you can do here is this combinational logic is basically saying I'm relating everything to your input alphabet. And then I'm making this next transition based on the design. So if I'm at 1 and the value I get in the combinational logic is 0, I'm going to stay in the same state here. So here's a Mealy machine. Mealy machine, here's where the difference is. The difference is here from your inputs, right? So the inputs both affect the combinational logic and your combinational logic on your output. So typically, in a Mealy machine, we're going to go over the fundamental. So you're going to have some sort of operation that's done in each one, and if you're going to see this 0 or 1. So you're either going to, basically what this means is based on the operation, it actually makes a decision on which state to go to, and that depends on your direct from input value. All right. So we're going to go into, so here's a Moore machine example. This is actually the example that Moore presented in his paper. So you have 3 states, Q1, Q2, and Q3. Initial start state is Q1. So if you have a input of 1, what that means is, I'll draw this out for those of you watching on the video later. If I have an input of 1, that means I'm just going to go right back to the Q1 state. If I have a 0, that means I'm going to go to Q2. Likewise, if I'm at Q1 and I want to go to, if I have a 0, I'm going to go to Q3. If I have a 1, I'm going to go back to Q1. And then if I'm in Q3, if I have a 0, I'm going to go to Q2. If I have a 1, I'm going to go to Q1. So that's how that works. And so here I've kind of given you the example, and this is example 1.1. Here what we're going to do is we start in our initial state S1, and I've given you a set of inputs. So remember we have, for our Moore machine, we have a set of inputs, and we have our state information, and what we're going to do is we're going to use that input plus the state information to determine the next state we're going to. So if you've blanked this out, so let me, I can go here and we can get wipe. We can hide all of this for the time being. So we have an situation where if we end up at the end of the input where S1 is true and S2 is false, find the final value. I'm going to hide all this, but okay. So if I'm at S1 and I have input 1, what am I going to do based on this Moore machine? Go to S1, right? So we can write our answers over here. So now I have a 0. Where am I going to go? S2. So I'm at S2. I know the answers are here. Pretend you don't see them, because you won't have those on a quiz or exam, right? So we're at S2 and we get a 1. What do we do? Stay. Now we get a 0. What do we do? It's 1, and then we get one more 0. S2. So we describe that as false. So if I have 1, and so let's say I'm at, basically what this means is 1, 0, 0, 1, 0, right? So basically, it's kind of inverting, right? So I can determine whether or not it's an input, right? So block that out. It's 1, 0, 0, 1, 0. So it's kind of an inverter based on, if you get a 0, it's going to invert. If you get a 1, you're going to keep the same value. So I've actually posted the full copy of Edward Moore's paper on machines like this. A student in my class last year who actually read this and got so interested, he started doing work with me on medical device security, because a lot of the Moore machines and Mealy machines have a lot to do with this. So that's the answer to example 1.1. This is the example that Mealy posted, right? So we have a Mealy machine. So we have different transitions. So we have 3 states, 0, 0. I'm sorry, we have 4 states, 0, 1, 1, 0, and 1, 1. So the notation on each edge, and this is where you're going to have your input plus your state information, is the X is the input value and Y is going to be your output value. So it's not, the output isn't just tied to what state you're in. It's actually going to indicate what your output value is. So for example, here I've given the example of this transition. So here we start at state 0, 1, right? And basically we have an input string of 1, 0, 0. So at 0, 1, and our first bit is going to be a 1, right? So we're transitioning to state 0, 0. But this notation 1/0, for those of you watching later on the video, this is 1/0. What that means is our input is 1, that correlates to this, right? And the output is going to be 0. So you're actually going to have an output string as well. So your first bit of your output string is 0. So when you get to 0 here, we're starting at 0, 0. Here we see that if we have the input of 0, so this says 0/1, right? So if you have input of 0, that means you're going to have output of 1. And then you go to this next state, 1, 0. And so this is the diagram here. So if you go 1, 0, and the third bit is 0, 0/0, so that means our output string is 0, 1, 0. So what this means is, and this is why it's a Mealy machine instead of a Moore machine, is that the state not only impacts what state you're going to, but what your output is going to be. Whereas with the Moore machine, and this is the answer to your question, with the Moore machine, the output is a direct correlation to the state you're in. Whereas with the Mealy machine, the input not only affects what state you're going to, but also the output string. Does that make sense? So we're going to go, this is example 1.2. So we have our incident where this is the finite state machine. This is another finite state machine. That's a Moore machine. So we start out at S0 here, and our input string is 1, 0, 1, 1, 0, 1, 0. And so we usually follow along. And so this says 1, 0. So our input is 1. And so our output string is going to be initialized at 0. We get to S1. We have the 0. So 0, we follow. I should go along with this so that you can watch later for your review. So you go here along with this. So that's where you get this guy, right? Again, you're in S2. You're going to have a 1. So 1/0. That means you transition to S1, and your output is going to be 0, which explains that. Next, you're going to have, you're in S1 again. So S1, you have an output of 1, which means you're going to stay in the state, and it's 1/1, which means it's going to correlate to 1, which is where we get this guy. And then the last three, S1 goes to 0, which goes to S2, which we've already covered, again, and then S1. So this one just starts going in, which makes sense because S0, you can only go away from the state, you can't come back to it, and you're either looping or staying in the same state. And again, I've also posted a copy of George Mealy's paper where he presented this as well. So you have a lot of historical information about where this came from and using the exact finite state machines from their papers. So this is how they hope to explain it to the world, so it's how I'm hoping to explain it to you. Does anybody have any questions on this before we continue? All right. So, getting a job when you graduate. So, we've just talked a lot about combinational logic, sequential logic, digital systems, why that's important. All right, so this is an actual job description that that's available right now on the National Instruments page. And it's a hardware engineer, and what I've done is gone through and highlighted all the things that you'll learn in this course that will apply to getting this particular job. BS in electrical engineering, computer engineering. I think that's what you all want, right? Yeah. I would hope so. This year, just taking this class for fun. Proficiency in synchronous design elements such as flip-flops, timing diagrams, and state machines. So you learn synchronous elements in Section 1 in more detail in Section 4. Programmable logics in all sections. Synthesis and design simulation, you'll do that in your projects. You'll learn about VHDL in 386, your lab for this course that you'll take next semester. And you'll learn C in this course. So programmable logic design, including VHDL or Verilog, synthesis and design simulation techniques, you'll learn all of that. Computer architectures and interfaces, you'll learn that in a lot of detail in this course. Sequential and combinational logic. Basic memory technologies and processor interfaces. Since it's an advanced digital systems course, we won't be learning about analog design interfaces, but I think you guys have other courses where you do stuff in analog. Understanding of computers and programming languages, example C, and assembly language. So you will actually be taking C code, turning it to assembly language, which will then turn into machine language, which proves understanding of computers. Interest in learning and working with digital and computing technologies. Okay. And then demonstrated ability to, and coding projects, you will cover all of this. Applying diagnostics to identify technical problems, propose viable solutions, and apply technical solutions. So I'll give you some creativity challenges. You'll work through those, code it up, write a report, get it done. Quickly learn applicable systems and technology. We'll be using LCC Win to compile C. Take initiative and be a self-starter. Hey. Work effectively in a team development environment. Take ownership of goals and tasks. Enjoy problem solving. Grasp fast-paced technical conversations. Okay, so can clearly and effectively communicate in English so you can understand others and others can understand you. Project reports may be used to justify this requirement. So taking this course, there you go. You can apply for a job right off the bat. And so I promise we're not just doing this. So here's where we're going to stop for the lecture portion. You're not dismissed yet. Hold on, let me stop the video. Let me ask you, does anybody have any questions before we do this attendance stuff? All right, so for your assignment, let me say what your assignment is. You have example 1.1 and 1.2 and TGOs 1.1 through 1.12, and they're due next lecture. So TGO 1.1 through 1.12 in examples 1.1 and 1.2. I will be uploading the video to YouTube. I'll send out the link and I will send out the assignment. Yes?
So the TGOs that are in our notes, so I guess we use those to complete examples 1.1 and 1.2.
Correct. The examples 1.1 and 1.2 are the ones on Blackboard. I should know. Last year, a student made the mistake of doing 1.1 and 1.2 in the textbook. All right, so let me close this out and